This video will look at the summer work packet, Kinematics. This section is designed to go over horizontal kinematics. And this will cover a lot of the formulas as well as some example problems to help you succeed. First, we're going to start off with some basic formulas. This is essentially putting into formula form what we talked about in another video. We have displacement. Displacement is going to be represented with delta x, or the change in your position, which is going to be the final position x minus the initial position x0. We're going to use this subscripting format. Instead of having an f down here, we're just going to have x that is the position at our end, and then we have x0 to represent our initial position. We also have velocity, which we're going to use to represent v with a subscript x, and that's equal to our change in position over time. Now, I wanted to really quick talk about the difference between average velocity and instantaneous velocity. If we have a position versus time graph that looks something like this, so it's a curved position versus time graph. If you remember, the slope of a position versus time graph is your velocity. So here we have our slope that is constantly changing. If we were to look just from the beginning to the end and find that slope, that would give us the average velocity. If instead we were to look at just one section of this graph and find a tangent line of that graph and find the slope of that tangent, that would tell us the instantaneous velocity. A lot of times we're going to be using average velocity. Sometimes we're going to be using instantaneous. It's important to note the difference and to read carefully to know when they are different. We also have acceleration. We're going to use an a with a subscript x to represent acceleration, and that is equal to the change in the velocity in the x direction over time. Delta Vx is equal to the final velocity, which we're going to call Vx, minus the initial velocity, which is going to be Vx0. Okay. A lot of our scenarios are going to be built around acceleration being constant, so all of our formulas are going to focus on when acceleration is constant. There are going to be some scenarios that we're going to work on where acceleration is not constant, but we'll be able to figure that out. So based on the formulas up here, we're going to actually build out some more useful formulas. We're going to derive some formulas. The first one we're going to start off with is the acceleration in the x is equal to, instead of writing delta Vx like I have above, I'm going to write Vx minus Vx0 over t. And now I'm going to rewrite this formula to solve it for Vx, so solve for the final velocity. I'm going to start off by multiplying both sides by time. It gives me axt equals Vx minus Vx0. Again, I'm still trying to isolate this, so I'm going to add Vx0 to both sides. That gives me a final equation of Vx, the final velocity, is equal to the initial velocity plus the acceleration times time. You can actually find this equation on the AP Physics 1 equation sheet under Mechanics. This is equation number 1. The next equation we're going to work on is trying to develop an equation for position, specifically the final position, so that we can figure out where an object is going to be at the end of its motion. Now, there are multiple ways to derive this formula. The easiest, however, is to start with a velocity versus time graph. If the velocity versus time graph looks something like this. So if we remember, the slope of this graph will be the acceleration. So we have an object accelerating. This velocity that it starts with, we're going to call v0x. This final velocity, we're going to call vx. And this length of time it takes to do this motion, we're going to call t. To find position from a velocity versus time graph, we need to figure out the area. So we need to figure out what this area is underneath the graph. To do this, I'm going to break it up into two shapes. I have a rectangle down here, and then I have a triangle up here. This will tell me the overall change in position. It won't tell me where I start and where I end, but it will tell me how much the object has moved. So I'm going to start off with the rectangle. To find the area of a rectangle, we take the width, which is t, and we multiply it by the height, which is v0x. Then we need to find the area of this triangle. In order to find the area of a triangle, we're going to do 1/2 of the base, which is t wide, times the height. Well, to find the height of this, I actually need to subtract vx and v0. And I'll add those two terms together. Delta x equals v0xt plus 1/2. Now this term here, vx minus v0x, that is just delta v, the change in velocity. Now, the change in velocity, if I look up here, I could rewrite this formula as delta vx equals axt. So I can replace my delta vx with an axt. I'm also going to go ahead and replace delta x here with the final position minus the initial position. With a little bit more algebra, combining these two t's and moving this x0 to the other side of the equality, I get an equation for x equals x0 plus v0 x t plus 1/2 at squared. This is another equation on your equation sheet. It's equation number 2. The last equation we're going to derive is the, you guessed it, third equation on the equation sheet. We're going to start off with remembering that acceleration equals delta v over t, and that time would then be equal to delta v over a. If you solve this equation here for t, get t by itself, you'll get this. We're also going to talk about average velocity. If we think back to that example I gave before of a position versus time graph, x in meters and time in seconds. To find this average velocity, we would just need to know what is the xf and what is, sorry, not xf, we're calling that x, x0. That would tell us the delta x over time. There's another way of finding the average velocity. If your acceleration is constant, you can find the average velocity just by taking the two velocities you have and dividing them by 2, which is just a basic average. Using this, we're going to go ahead and get started. I'm going to first start by cross-multiplying. So I get 2 delta x on one side, and I have t times vx plus v0x. Then I'm going to take this equation here and plug it in for t. So 2 delta x stays the same. Everywhere I see a t, I'm going to replace it with delta v over a. Now I don't like having this a in the denominator, so I'm going to multiply it over to the other side. 2a delta x equals delta v is going to be equal to the final velocity, which is vx, minus the initial velocity, which is v0x. So I can replace my delta v in the equation with vx minus v0x. I'm still multiplying that by my sum of the two velocities. If we were to multiply that out, we would actually end up with vx squared minus v0x squared. So that gives me 2a delta x equals vx squared minus v0x squared. If I solve this equation for my final velocity, vx squared equals v0x squared plus 2a, and I can replace my delta x with final position minus initial position. This is the third equation on your equation sheet. So those three equations, while they are complicated, they all come from the same basic formulas. Do want to draw your attention that these equations only work when a is constant. If acceleration changes during the object's motion, so for instance a car starts accelerating and then it starts to brake, or a runner slows down. A runner's running at a constant velocity and then slows down. If that happens, you're going to need to approach the question a little bit differently. Typical variants of these equations. The first equation, we don't typically see this variant very often, but I can combine, anytime I have two velocities, the final and an initial, I can actually combine it into a delta v. So the change in the velocity is equal to the acceleration times the time. I can take this second equation and I can do something very similar. I can take this x0 and x and combine them into delta x. This is usually a much more useful equation. A lot of times this x0 will be 0 by itself, so it ends up falling out of the equation. But oftentimes we're more interested in how far we move than our final location. And then this last equation, this last term right here, we can just replace it with a delta x. I do want you to note that vx squared minus v0x squared is not the same as delta v squared. Delta v squared, I'm going to do that over here, would be equal to vx minus v0x squared, which would be vx squared minus 2 vx v0 plus v0x squared. So you note that's not the same. So you do have to be careful. Okay, we're going to go ahead and get started with some sample problems. Okay, here we have two scenarios. We have a car accelerating from rest. From rest means that v0 in the x direction is going to be 0 meters per second at a rate of 2 meters per second squared. 2 meters per second squared would be our acceleration for 10 seconds. 10 seconds is the time it takes. How fast is it moving at the end of the 10 seconds, and how far has it moved in these 10 seconds? A good rule of thumb is to always draw out your scenario. So here is my car. It starts off at rest. Its acceleration is 2.0 meters per second squared forward. We need to figure out how fast it's moving at the end and how far it's gone. Once we have a picture drawn, we're going to write out our variables. Most of our kinematic problems are going to involve these 5 variables that we saw in our formulas. The change in position, the initial x velocity, the final x velocity, the acceleration in the x direction, and the time. If we don't know a variable from the word problem, we're going to give it a question mark. If it's something that the problem is asking us to solve for, we're going to give it 2 question marks. Then we're going to look at our equations. When I look at my equations, I see that there is this equation. I know that this is an equation I'm going to want to use because I know what v0x is, I know what acceleration in the x is, and I know what time is. The only thing I don't know is velocity in the x, and that happens to be my first question. How fast is it moving? Normally I would take a step and solve the equation for the variable that I want, but it's already solved, so we don't need to worry about that. I'm going to plug in my numbers with units. Plug it in, and I get a velocity in the x of 20 meters per second. My second part, delta x equals v0t plus 1/2 at squared. This is the equation I'm going to want to use. Again, I know what v0 is, I know what t is, I know what a is, I know what t is. The only thing I don't know is the distance that it travels, or the displacement it has. Again, I would normally solve for my variable in question, but it's already done for me. A lot of times when I do these problems, if there's a variable that is equal to 0, I will cross it out. So because this v0 is 0, doesn't matter what the time is, 0 times some time will always be 0. So it just falls out of the equation, leaving behind the 1/2 of my 2 meters per second squared times 10 seconds squared. 10 seconds squared, that's 100 times 2 divided by 1, or multiplied by 1/2, gives me 100 meters. So this car has accelerated to a speed of 20 meters per second, and it has traveled 100 meters in order to do so. Our next problem, we have a runner accelerating from rest at a uniform rate. So from rest, v0x equals 0 meters per second. A uniform rate just means a is constant for 2.5 seconds. That would be our time. To travel 20 meters. 20 meters would be our delta x. We need to find the acceleration of the runner. So again, we're going to draw our picture. There's our runner. We know their velocity is 0 meters per second. We want to find their acceleration as they're traveling. And in doing so, they cross a distance of 20 meters. Now I'm going to write my variables like before, delta x, v0x, vx, a, and t. I'm going to plug in what I know. My displacement is 20 meters. My initial velocity is 0 meters. My final velocity, I don't know. I'm only giving it one question, though, because the problem did not ask for it. My acceleration is a question mark that I'm trying to solve for, so I'm going to write 2 question marks. And then we have 2.5 seconds for the time. I'm going to use the equation delta x equals v0xt plus 1/2 at squared. I know the delta x, I know v0x, I know t. The only thing I don't know is a. But in this equation, my v0 is 0, so that is going to go away, like I mentioned before. So that leaves me behind with delta x equals 1/2 at squared. Before I plug in numbers, I'm going to isolate the variable that I'm trying to answer the question about. I'm going to get rid of this 1/2 by multiplying everything through by 2. Gives me 2 delta x equals at squared. Now I have to get rid of this t squared. I'm going to divide both sides by t squared. That gives me acceleration is equal to 2 delta x over t squared. Now I can plug in my numbers. 2 times 20 meters divided by 2.5 seconds squared. When I plug it in a calculator, I get 6.4 meters per second squared. This next problem is a much more difficult one. We have an object accelerating from rest. So again, from rest, v0x equals 0 meters per second at a rate of 10 meters per second squared. That's our acceleration for 15 seconds time. Before moving at a constant velocity. Constant velocity means acceleration is going to change. Acceleration will now be equal to 0 meters per second squared. If the velocity is constant, it means it's not changing. If the velocity is not changing, we are not accelerating. For 20 seconds. That's another time. How far does the object travel? Now, if you remember from a few minutes ago, I said that the equations we've been working with only apply when acceleration is constant. I have an acceleration of 10 meters per second squared that then all of a sudden stops. So we're actually going to look at this problem in 2 steps. We have our object. There's my object. Has an initial velocity of 0 meters per second and is doing this for 15 seconds. And is going to move over here to where the acceleration is 0 meters per second, and it's traveling for 20 seconds. For this time, it's going to travel some distance that I'm going to call delta x1, and over here it's going to travel some distance, which I'm going to call delta x2. Delta x1 is going to be my first variable, v0x, vx, a, and t. I'm going to fill in the numbers that I know. I know it takes 10 seconds over here, or not 10 seconds, 15 seconds. Accelerates at a rate of 10 meters per second squared. I don't know what the final velocity is for this section, but I do know the initial velocity is 0 meters per second, and I don't know how far it travels. However, that's going to be important. I want to know how far does the object travel. So I need to know this delta x1 and this delta x2. Over on this side, I have delta x2, v0x, vx, a, and t. The only bits of information I know, though, are the acceleration is 0 meters per second squared, and that the time is 20 seconds. I don't know either of the velocities, but because acceleration is constant, or is 0 here, I know that those two have to be equal, those two velocities. Also, if I think about this, when the object is accelerating through this motion, it will speed up to some final velocity. Then it stops accelerating and starts to continue on at a constant velocity. The final velocity for the first section will be equal to the initial velocity for the second section. So if I can find what this is, that would be the same as those two velocities. Okay. I'm going to look at my equation sheet. And I'm going to look at this equation. I know V0, I know T, I know A, I know T. In fact, V0 is so nice because V0 is 0, so it goes away. leaving me with delta x equals 1/2 10 meters per second squared times 15 seconds squared. Plugging in my numbers, I get 1,125 meters. Let me write that a little neater. So I already know half of my answer. I know that while it's accelerating, it travels a distance of 1,125 meters. On the other side, I could try to use the same equation. Only over here, it's acceleration that is 0. So this whole term at the end goes to 0. Unfortunately, while I know the time, I don't know the initial velocity. I know the initial velocity way back over here, but I don't know the initial velocity here. In order to figure out that initial velocity for the second part, I need to find the final velocity for the first part. Vx equals v0x plus at. This part is 0, because the initial velocity of the first motion is 0. Meaning I can just plug my numbers in, and I get a final velocity for the first motion of 150 meters per second. That will become the initial velocity here. Delta x equals 150 meters per second times 20 seconds. Meaning delta x2 is equal to 3,000 meters, or 3 kilometers. Finally, to get the final answer, I need the total delta x, which would be my delta x1 plus my delta x2. My total would be 1,125 meters plus 3,000 meters, giving me 4,125 meters for this object. So whenever the acceleration changes, we just have to be careful to subdivide into before the change and after the change. You'll note I kept everything before the change over on the left and everything after the change over on the right. And the last question we have here. We have a motorcycle moving at a constant velocity of 10 meters per second. The phrase constant velocity tells me that the acceleration is 0 meters per second squared. As it passes a car at rest, we have a car at rest. If the car can accelerate at a rate of 2 meters per second squared, how long will it take for the car to catch up to the motorcycle? So this is asking us how long. Time equals question mark. Here we have two different objects. We have our motorcycle and we have our car. Just like before when we had two different accelerations and I separated them, this time I'm going to separate our two different objects. We have our motorcycle. We know that the v0 and the x is 10 meters per second, and we know that their acceleration is 0 meters per second squared. They're just moving at a constant velocity. In doing so, they travel some distance, and it takes them some time. Then we have our car. Starting at rest, v0x is 0 meters per second, but they can accelerate at 2 meters per second squared. They're going to end up at some final velocity that we don't know as they're moving through this motion. They're also going to travel some distance, and they're going to take some time. Now we have to think about this. How long will it take for the car to catch up to the motorcycle? Well, what is the definition of catching up? It means that you're in the same place at the same time, or you've traveled the same distance. At the same time. We're going to go ahead and subdivide our work over here. Everything on the left is going to be motorcycle. Everything on the right is going to be car. If I were doing this in my notes, I would actually color code and have different colors, one color for motorcycle and one color for car. We know that the motorcycle is moving at a constant velocity, so their initial and final velocities are the same. And the time is what we want to know. Don't know the distance traveled for the car, but we do know that they start from rest. They move up to some final velocity. They're accelerating at this rate, and it's going to take them some time. So, I'm going to pick equations. I'm going to pick this equation for my motorcycle, simply because acceleration goes away. Over here, for the car, I'm going to use the same equation, but I have to be careful because there are different starting values. My velocity is 0, so that is going to go away. Now, remember, we're trying to figure out how long it takes the car to catch up to the motorcycle. We're trying to find when these two delta x's are the same. So I'm going to set them equal. If I set these two delta x's equal, that means the other sides of their equalities have to be equal. Again, left side is all motorcycle, right side is all car. From this, I see I've got the same time on both sides because the time for both objects is going to be the same. So I can divide both sides by t, canceling it out over here and canceling out a square, which is really nice because no one wants to work with a square. Here I'm trying to find the time, trying to isolate the time. So now it's going to get a little messy, and this is where color coding would help. But I just have to remember that the acceleration is for the car, and that the velocity is for the motorcycle. And I'm going to get time all by itself. I'm going to start off by getting rid of the 1/2 by multiplying both sides by 2. Then I'm going to get rid of the a by dividing both sides by a. Now I can plug in my numbers. 2 over 2 cancels. That leaves me with 10 seconds. Just a quick note on the unit. We have meters per second divided by meters per second squared. Dividing by a fraction, meters over second, is the same as multiplying by the inverse. Meters cancel, second cancels with one of those, and we're left with just 10 seconds as our final answer. Now I know I went through a lot of these examples pretty quick. The first two are more similar to what you will see in the packet. The second two are more complicated. They involve a little bit more thought. That's more of what we're going to need to work on when we come back from summer.